Um, so the title for this course is Trigonometry. I'm going to post these to PowerSchool so that if you need to look at it again, or if you're absent, obviously everyone is here today, but I'm going to try to do that throughout the year for all of our lectures. Since the classes are so long, if you miss a day, you might not see me for a day or two. It just seems easiest for everybody to try to do that. This course is called Trigonometry. If we break the word trigonometry into two parts, like two words, what are the two words that we probably naturally want to break that into? Probably trig and then ometry, right? Everybody feels like that's the natural way that you'd try to break this word up if you're trying to understand it. What do you think that trig part is referencing? What do you think that means? You guys can just take guesses. This is not... I know you said something under your breath, but it wasn't loud enough for me to hear. But that's okay. It's okay to be wrong about things. It's not a big deal. Take a risk. It's okay. Yeah, triangles. Yeah, it's exactly what the trig part is referencing, is triangles. Okay? And then the ometry part is a suffix we've seen a lot, right? What do we think that part is referencing? It's like study of. It's basically, we're talking about the study of triangles here. So, it's this topic that I want to kind of focus on at the beginning when we go sort through kind of the prior learning that we have that'll be relevant in this course. So, what previous course have we talked a lot about triangles in? Geometry. It is geometry. So, when you guys think about triangles in geometry class, let's kind of review some of the things that we know about triangles, or we remember about triangles, from our previous geometry class. So again, I'd really like you guys to think about what you remember and volunteer some of the things that you remember about triangles. And if you're not quite right, that's okay. We'll adjust it so it is correct. And if all you have is like a vague idea, that's okay. Or if it's just a word, that's okay. We'll kind of fill in the blanks. But this is an exercise, hopefully, to get us kind of memory jogged, because I know geometry was a long time ago, right? But just to jog our memory about some of these ideas that are going to be relevant to us this year. Okay? I have a volunteer that remembers anything about triangles from geometry. Okay. That's true. Now, this formula is nice and compact and simple, right? Matt remembers it 2 years later, which is lovely. The problem is that if I draw a triangle like this, where's the height? Is the height one of the sides? No, right? The height is like that line that kind of comes from the vertex and intersects the other side at a 90-degree angle. If we don't know what the height is, that formula is pretty difficult to use. one of the things that we'll do in this course is create a new area formula for a triangle that we can use if we don't know the height explicitly. But this is kind of the foundational. The formula, the new formula that we'll create looks a lot like this. It just has a little bit of a fudge factor kind of built into it that corrects using one of the sides instead of the height explicitly. But that's a good thing. Yeah, we absolutely relevant. Caitlin? Excellent. So this is, of the things from geometry related to triangles, is probably the most relevant topic or most relevant thing that you could remember for this course of trigonometry. So Sohcahtoa is an acronym. It's basically a mnemonic device to help us remember some formulas. What Sohcahtoa stands for is that sine of angle x is equal to opposite over hypotenuse. So the S is for sine, the O is for opposite, the H is for hypotenuse. The next three letters, CAH, is cosine of angle x is equal to adjacent over hypotenuse. And then the last three letters, the TOA, is tangent of angle x equals opposite over adjacent. So if there is one thing from your geometry course that you remember that is going to be useful to us going forward in this class, Sohcahtoa is absolutely the best thing to kind of have remembered. This will use the heck out of this. Quick question in regard to this. When we talk about opposite, adjacent, and hypotenuse, what are we referring to? Sides of a triangle, but not just any old triangle. It has to be a special kind of triangle. A right triangle. That's correct. So if this is my right triangle, and this is my angle x, and say I'll name the vertices A, B, and C, which one of these three sides do I mean when I say opposite? So I need to be looking at angle x. Which side is opposite angle x? Matt? Yeah, it's side CB. This is my opposite. Very good. And which side is my adjacent? AB. And then which side is the hypotenuse then? Obviously AC, right? And if I was talking about this angle, angle Y, the hypotenuse is obviously still the hypotenuse, right? What does hypotenuse mean again? Which side of the triangle is the hypotenuse? Well, it's the longest side. Yeah, right. So in this case, certainly it's the one across from the right angle, but in general, it's just the longest side. If we're talking about this angle Y, though, AB is now the opposite side, and BC is then the adjacent side. So depending on which angle in the triangle we're focused on, the opposite and adjacent might be different. Everybody kind of remember that? Good. Let's stick here on Sohcahtoa a little bit longer because I have some more kind of guiding questions for us to kind of jog some memories out of. So what I want to talk about here is what values of x can I take the sine of based on this definition of Sohcahtoa, or this definition that we're working with. So remember, x is an angle measure inside of a right triangle, correct? That's how we've defined this x. So what values of x can I use there? Is there a smallest value of x? What's the smallest value that this x could have in this right triangle? About 0, right? You can't have an angle measure that's 0 or smaller and still have a triangle. Everybody agree with that? Is there an upper bound on that value of x? Is there an angle that you can't be bigger than 90? That's correct. Matt, do you remember why you can't have an angle bigger than 90? Or a second angle bigger than 90 in the right triangle? There you go. Yes, that was what I was looking for. So that theorem had a name. It was called the triangle sum theorem. But it basically says that the interior angles of a triangle add to 180 degrees. So the way we've defined sine, cosine, and tangent here, I can only use sine, cosine, and tangent on angles between 0 and 90 degrees. One of the first things that we're going to do in trigonometry after we do a little bit of introduction is redefine how we're describing sine, cosine, and tangent so that we can take the sine, cosine, and tangent of an angle of any size. So right now we're locked into using angles between 0 and 90 degrees, which is nice, but we want to be able to really use sine, cosine, and tangent on angles of any size, and that's one of the first things that we're going to do in this course is generalize our definition so that we are able to do that. Everybody okay with what I mean by generalize? So right now we have a narrow definition. We want to change the way that we're defining sine, cosine, and tangent and take it from being linked to these right triangles and giving it a little bit of a broader definition that still includes this Sohcahtoa definition, but allows more to encompass a little bit more, right? So like dogs are mammals, right? Dog is a subclass of mammals. The mammal is the broader, the more general term for what a dog is. So like Sohcahtoa is like the dog, and this new definition is like the mammal. It's going to include what we had before, but also extend things outward so we can include more angle measures that we can use sine, cosine, and tangent on. Okay with that idea? And we'll talk much more about that in much greater detail later, but that's coming. Okay. What other triangle things do we remember from geometry? Do you remember any triangle-related vocabulary? I'll start with one to kind of jog our memories. Yup, okay. Yup. Scalene. Yep, that was in one. Isosceles, and I apologize right now, I'm most likely spelling this wrong. There's one more that I would expect you guys to come up with. An E. That's the one. And then there's one more that I would have been surprised had we come up with. Equiangular. Let's just take a quick moment and talk about what these what the definitions are for these names. As it's been a little while, make sure we're all on the same page. Acute. When we talk about an acute triangle, we mean all the angles are less than 90. Very good. Obtuse. What do we mean there? We have one angle greater than 90 degrees. Can we have two angles? No. Why not? Has to add up to 180. That would be too much if we had two angles that were greater than 90. Very good. Right. One angle is 90 degrees. Can we have more than one angle 90 degrees? Nope. Why not? Has to add to 180. Good. Scalene. This is the one that everybody kind of seems to forget. It just means that all the side lengths are different. So, for example, like if you have a triangle with side lengths 3, 4, and 5, that's a scalene triangle. Isosceles. Exactly. Yep. Two of the sides are the same. That's perfect. Equilateral. All three sides are the same. And then equiangular. All three angles are the same. Now, is there a difference between equilateral and equiangular? No. So one of the other facts that we have from our geometry class is that in a triangle, the side lengths are proportional to the angle measures, and the angle measures are proportional to the side lengths. So if all the side lengths are the same, it would mean that all the angles have to be the same as well. And if all the angles are the same, all the side lengths are the same. That applies similarly to an isosceles triangle. So in an isosceles triangle, we said two of the side lengths are the same. We can also then say that two of the angles are the same. Everybody okay with that idea? So I'll write that as a note real quick. And I should probably say and vice versa. Do you guys know what I mean by vice versa there? That we just trade the position of side length and angle measure. You know, that angle measures are proportional to side lengths and side lengths are proportional to angle measures. That it works both directions. Okay. So if we go back and talk about Sohcahtoa for a minute, if I'm using Sohcahtoa, I have the requirement that I have to have what kind of triangle? a right triangle. Do you guys remember if there was a way to use sine, cosine, and tangent on non-right triangles? I don't remember in regular geometry if you talk about this or not. Nobody seems to recall. Okay. Do the name law of sines or law of cosines sound familiar? That maybe sounds a bit more familiar. Probably didn't do a ton of work with those in your geometry class. We will go over this topic as if no one had seen this before inside of this course, but we'll talk more about the law of sines and law of cosines in much greater depth later on this semester. But that was a topic that would have come up, I know for sure, in the honors geometry class. It's been a long time since I've taught the regular geometry class. I can't remember if you guys covered that there or not, as my suspicion is many of us are coming from the regular geometry class 2 years ago. And if you didn't cover that, we'll certainly do it in great detail. But there is a way to deal with, or a way to use sine, cosine, and tangent inside of non-right triangles. And those are the tools that we use there, the law of sines and law of cosines. There's one more very important triangle fact or theorem or whatever you want to call it that nobody's mentioned yet that I'm a little surprised by. It's one that I'm sure that you've used many, many times and are quite comfortable using. The Pythagorean theorem. Yeah. So, anybody remember the formula for the Pythagorean theorem? Very good. And what are A, B, and C? The sides of a what kind of triangle? Right triangle. So does it matter what side we assign for A, B, and C? Yes. Which one does it matter? C must be which side? The hypotenuse. We can assign A or B to either leg. It doesn't matter there. But C must be the hypotenuse. And the hypotenuse, again, is the longest side. Okay. Notice here that the Pythagorean theorem is stuck using what kind of triangle? Right triangle. Would it be nice to be able to use the Pythagorean theorem for any kind of triangle? Yes. That is essentially what the law of cosines is. The law of cosines is essentially the Pythagorean theorem with a fudge factor built in so you can use it on a non-right triangle. If you try to use the law of cosines on a right triangle, it just turns into a squared plus b squared equals c squared. So that is essentially all the law of cosines is. It's just a modified version of the Pythagorean theorem so that it works for all triangles. Is everybody okay with that idea? You need some extra information to be able to use it, but it works for all triangles. Caitlin? Of course. Okay. Any more triangle things that you guys can remember from geometry? Okay. I think this is probably all the major stuff we kind of came up with here eventually from between the class. So that's pretty good. One of the things, though, that we're going to do in trigonometry is we're going to spend quite a bit of time talking about sine, cosine, and tangent. But instead of thinking about them as just an operation, like something we do on our calculator, we're going to think about them as a function. So, what course did we spend a lot of time talking about functions in? Algebra 3-4, right? So let's recall some of the things that we know about functions from Algebra 3-4. Does anybody remember the definition we gave for a function? I know, it was a long time ago. But I feel like this was something we hit pretty hard for a long time in that class. And if you don't remember it exactly, like that's okay. Well, if you're close, we'll fix it up so it is, so that we got it correct. But take a minute and think about what you think that definition is. And if you think you're close, or you think you got it, shout on out. Take a little bit of a risk. It's okay. There's no penalty for being wrong. I guarantee you, if you're not quite right, there's plenty of other people in the class that are like, that's what I was thinking too. And it's okay. What was it kind of like? What did that definition involve? Very good. Yeah, so it's talking about pairing up x's and y's. Yep. It was how we're doing the pairing, though, that was the important part, right? So when we think about what a function looks like, we have ordered pairs. So our ordered pairs, every x pairs with exactly one y. So that's the extra little piece of criteria that we need for something to be a function, is we can't have any repeated x coordinates. Each x has to have its own is just used once. Maybe is the easiest way to say that. Does that sound familiar now as we mentioned that? Good. So we spent a lot of time in Algebra 3-4 talking about functions, and we talked a lot about different ways that we can describe a function or the different features of a function. Does anybody remember any of those descriptors? There were two things we asked about with almost every different kind of function we talked about. Specifically, when we talked about the graphs of them, there are two things we almost always asked you guys to find. One of them started with a D, domain, and range would be the first two I'd be thinking about. So when we start thinking about these trig functions as functions, after we've redefined them, we're going to talk about their domains and ranges. What else did we talk about? This would be very early on in first semester. Well, even before factoring, though. That is true. We did talk a lot about factoring. Sure. So most of these terms that I'm looking for right now, we are looking at graphs and describing kind of what we saw in the graphs. So you remember the little man walking on the graph? Talking about that. What was that in regard to? Yeah, so if it goes up or if it's going down, which is the words we used there was increasing or decreasing. So that's the kind of the part of the class that we're talking about right now, is when the little man was walking on the graph, which is funny that I can describe that and you're like, oh, I remember that now. But that's good. Yes. Mm-hmm. Sure. So that is for describing similar or congruent triangles. Those are theorems to prove that two triangles were similar or congruent. And that's perfectly, yep, that's certainly a thing, and that is prior learning, and that is actually something we'll use when we talk about the law of sines and the law of cosines, because it's the easiest way to tell which one of those two formulas you'd want to use is based on whether it's like an angle side angle or angle angle side, etc., which one of those situations you're kind of falling into. With regard to to increasing and decreasing, we also talked about maximums and minimums, like the highest and lowest point on the graph, right? Because that's where the graph changes from increasing to decreasing, is at a maximum or minimum. Do you guys remember that? There was another thing that we talked about alongside increasing and decreasing. Was it pair like that? It was positive and negative. So the graph was positive when it was above the x-axis, and it was negative when it was below the x-axis. We talked about the intercepts. So like the x-intercepts or the y-intercepts, where the graph crosses the x-axis or y-axis. Those were other things that we talked about. And all of this will kind of be relevant as we build out sine, cosine, and tangent into their own trig